because it combines our frequent item sets method with the method we have seen for finding communities in graphs. So for analyzing graphs, we can use a version of the frequent item sets market basket analysis in order to find these small, dense parts inside of the graph. So the idea is, given a web graph it's web graph, the nodes are web pages and the links are hyperlinks that link to other pages. So this is similar to when we did the PageRank algorithm. We want to find small communities in this graph. And the small communities are defined as parts of the graph that are densely connected with each other. So this is a two-layer graph because we have one layer on the left and one layer on the right. And if you remember the topic of hubs and authorities, this is very similar to the hubs and authorities. Remember, the hub was a website which it has many links to the information pages, authorities. So for example, the hub could be the university's website that has links to all the faculty websites that have all the syllabus, lecture notes, exercises, and other information on them. So this came from when we were talking about hits and hubs and authorities. This is very similar idea. So we have a set of hubs that point to a set of authorities. So if they are densely connected, the idea is that these people are talking about the same subject. So how are we going to use this frequent item sets method? So we will enumerate a complete bipartite subgraph. What does it mean bipartite? It means it has two parts. It has part one on the left and part one on the right, and part two on the right. Complete, it means that it has every node on the left has edges to all the other nodes on the right. That means that it's complete. It's a subgraph because that's only a part of the web. Right? We are looking for small parts of the web that are densely connected to each other. We will call that KST, where S is going to be a support threshold and T will be the number of items in the set. So this is going to be the number of nodes on left. Because we have 3 nodes, then this support threshold is equal to. So this S parameter is equal to 3, and 4 is the number of nodes on the right. That is cardinality of a set. Cardinality of a set is the number of items in the set. In this case, we have 3. 1, 2, 3. So the goal is to identify all fully connected subgraphs with given these two thresholds, S and T. So 3, 4 means that we have 3 nodes on the left linked to 4 nodes on the right. That's what that means. Each of the 3 nodes on the left links to all the nodes on the right. That means that the graph is complete. And to find these kind of parts of the web, we're going to use the FequentItemSets method. We already know how the FequentItemSets works. FequentItemSets is used for market basket analysis. So before, when we looked at that FequentItemSets, we have used that for a transactional database. So the data consists as a set of transactions. The universe is all the items. In the basket, a person can place some of these items. So they're gonna put some of the items in their basket. That is the set of items the person bought. And we have a support threshold. The support threshold in this case is F. And the goal is to find a subset which are called the FequentItemSets. That meet the minimum support threshold. So FequentItemSets which meet the minimum support threshold. So how are we going to use this method to find these kind of subgraphs on the web? Bipartite, which means they have 2 parts, one on the left and one on the right. So each node, we will view it as a set, and the node will be considered our market basket. So the node is going to show some items inside of it. So basically, the node has some other nodes that it points to, and these will be our transaction that we have seen before. So these are the items inside of the set for the node I. So the node I, the set for that is ABCD because it points to those ABCD nodes. So the set for node I is equal to ABCD. So this complete bipartite graph has 2 parameters. S and T. S is the minimum support and T is the item set size. So what will be S and T for this little graph here? This is the bipartite graph. It has 2 parts, part 1 and 2. It's complete because it has links. Each node has links to all the other nodes. Each node on the left has links to all the other nodes on the right. So it's a complete graph. What will be S and T here? So we want to find frequent item sets of size 4 because there is 4 items here. So the item set size will be 4. And minimum support will be equal to 3 because we have 3 nodes in the left side of the graph. So K here is 3, 4. Size is 4 because it points to 4 things on the right. And minimum support is 3 because we have 3 nodes on the left. So what are we going to do with the 3 nodes? For each of the nodes, for each of our nodes, we're going to create the item sets like that. So this node points to A, B, C, D. So we're going to create item set. And then we will find which of those item sets are frequent. And we want to find frequent item sets. So for every node, create an item set with minimum support will be equal to 3, and the minimum item set size will be equal to 4. But we can change these numbers. We can choose a different number here. And the idea is that we want to find the item sets that are considered frequent will meet these thresholds. So if we find, for example, if we find a frequent item set that is equal to ABC with support S, this means there are S nodes that link to this ABC. So if the support is equal to 3, it means there are 3 nodes altogether that point to ABC. So X is one of them that points to ABC, Y is another one, and Z is another one. So there's 3 of them. There are at least 3 other nodes that point to ABC as well. So we have found the bipartite subgraph called KST with nodes XYZ that point to ABC. Now, if we can, let's look at another problem. If we have a graph, we want to find all the frequent item sets. Find all the frequent item sets. Support threshold is equal to 2. So from this graph, we want to generate frequent item sets. All the item sets we have are these. That's because A points to C and B and D. So A is B, C, D. B points only to D. So B set for B is D. C points to B, D, E, and F. So these will be the set for C, and so on. For the entire graph, we're gonna generate item sets and see which ones are frequent. Well, they are frequent if they meet the minimum support threshold. They are considered frequent. So which subsets of these are going to meet the minimum support threshold? Well, we have to follow the algorithm, the a priori algorithm for finding the frequent item sets and see what is the support for each of the sets and subsets. And once we do that, we will see that B and D support is 3 because we have them 3 times in the data set. And for E and F, the support is 2. These are the only two that are considered frequent because they meet the minimum threshold. So, how do we generate the bipartite graphs for these? We have 3 nodes. If the support for B and D is equal to 3, this means that we have 3 nodes that point to B, D. Because support is equal to 3. So as you can see, this is BD, this is the second part of our graph, and there are 3 nodes that point to them, A, C, and E. For the other set, EF, the support is 2. This means we have 2 nodes that point to EF. So that's the second part of our graph. And so the 2 nodes are C and D that point to them. So these are the graphs that have 2 parts that are called bipartite. Subgraphs of these are the bipartite 2 parts graphs of the main graph. So that's how we can use the frequent item set method to find these bipartite subgraphs. What kind of communities we can find in web graphs? Here's an example of what kind of nodes what are these ABC nodes? These are some websites that are on a particular subject. So what kind of communities can they belong to? So here is an example. Rural Fire Service Internet site points to New South Wales, Australia links for some other websites links. So all of these nodes point all to these other nodes. This is the first part of the graph, and that is the second part of the graph. So this is just an example of these web pages and another web pages that they point to and what these pages are. It does not have to be web pages. These could be other things. These could be animals, for example. So it could be which animal is related to which other animal, or which animal is hunting and eating what other animals. So in this case we have a directed graph. So directed is when, if we have a directed graph, it's going to show that, for example, let's say this animal is eating this other animal. That's a predator for this other animal. Or in the case of friends, it could be the way the friends requested each other. So if there is no arrows, it's an undirected graph, and if it has arrows, it's directed. And so a node can send an edge or it can receive an edge. Let's say you send an invitation for someone to become our friend, or we receive a friend invitation. So in that case, we're going to have this additional information, whether we requested to be friends or somebody asked us and requested us to be their friends. If we take the Facebook friendship table, if that's the case, we need it, instead of one matrix, we're going to have two matrices. First is for outgoing requests, and the second one is for incoming requests, which are requests to become a member of a particular community.